Let's take a look at this and see how you did. Make sure everybody's on the same page here. What do f of x equals x squared and g of x equals the square root of x have to do with each other? Who can tell us?
Inverses.
What are they?
Inverses.
They're inverses, okay? They are inverses, okay? Let's see, trig functions, so we learned this in chapter 1. Trig functions take what? Angles and give ratios in return. So we put in an angle that tells us what the ratio of those particular sides are. Inverse trig functions, they do the opposite, right? So they're going to take ratios. We're going to put a ratio in there, and it's going to give us an angle in return. And then the next sentence there. Functions are inverses if they what? So let's pick the right word here.
Reverse.
Reverse, that's not bad. Cancel, not bad. I heard another one. Contradict probably wouldn't be the best one. I heard something over here. Undo, okay? If they undo each other. So whatever one function does, the other one undoes it. So this one squares, this one takes the square root. If we plug a 3 in here, this will turn it into a 9. If we put a 9 in here, it'll turn it back into a 3. So they undo each other. Okay, now you'll remember from 1050 that you studied a special type of function because its inverse was also a function. It was called a one-to-one. One-to-one function. Okay? Now, you remember what a one-to-one function was. It had to be a function, so it had to pass the vertical line test. What was a one-to-one function? How could you tell if it was a one-to-one function? Elizabeth?
The only one x equals that y and that y only equals that x.
Okay, so each x corresponds to only one y and each y corresponds to only one x. So every x corresponding to only one y, that makes it a function. If we do that in reverse, every y corresponds to only one x, that makes it a one-to-one function. We can also tell graphically whether or not a function is one-to-one. Is that a one-to-one function? It's not, right? Because it doesn't pass the horizontal line test. It passes the vertical line test, so x squared is a function. It's just not a one-to-one function. So what we do with these, this is not quite true that these are absolutely inverses of each other because we have to restrict the domain of this one, restrict the domain of x squared so that when we find its inverse, the square root function, they are indeed reflections across the line y equals x. Everything that used to be an x got switched into a y and vice versa. Okay, remember those discussions from 1050? Okay, because we're going to use that same idea in order to talk about the inverses of trig functions. And this is going to kind of support some of the stuff that we learned in chapter 1. So let's talk about the two-step process for finding the inverse of a function. What's the first one? Okay, switch the x and y. Okay, we're taking care of reversing those, reversing that order. And then what do we do next? Solve for y. Okay? Now, we're going to find the graphs of the inverse trig functions, and we're going to start with sine x. All right? So it says graph y equals sine x and restrict the domain in a reasonable way so it covers the same range. So I'm just going to draw a sketch up here. You don't have to draw anything on your paper. Just a quick reminder, this is what sine looks like. Okay? Now, if we're talking about a function, is that a function? It is. Okay, what's its domain? Okay, its domain is from negative infinity to infinity, right? You can plug in any angle you want and it will tell you what the ratio is. So its domain is from negative infinity to infinity. Okay, now what's its range? Negative 1 to 1. It goes from down here up to here, right? Okay, so that is a function. It has a domain, it has a range. The problem with this is it a one-to-one function? It's not. Okay, it's not a one-to-one function. So what we do is the same type of thing that we did with x squared. We're going to restrict the domain so it does pass the horizontal line test, but we're going to do this in a fairly clever way. We're going to think about how we do this. We still need to cover everything from negative 1 to positive 1. If I'm going to lop off part of this graph, in fact, I have to lop off a bunch of this graph in order to make it 1 to 1. In fact, I can only include about a half a cycle, right? About a half a period. where would be the most reasonable way to restrict this? Instead of going from negative infinity to infinity, where do you want to lop this off so it's still a function, still covers the same range? Okay, let's go 0 to pi halves. If we go from 0 to pi halves, that would cover this much. That only covers from 0 to 1, right?
Negative pi, positive pi.
Okay, I hear a bunch of mumbling. That's good. You're all thinking. Okay, I think I heard the right answer. The right answer is to go from here up to here. So to go from negative pi halves over to pi halves. Okay? Does everybody agree that if I take from here up to here, okay, that's a really crappy graph. We're going to clean it up in just a second. Would that be a one-to-one function? And would it cover from negative 1 to 1? Would it still cover the range that sine covers? Okay, so let's come back down here to this nice looking graph here. It says graph y equals sine x. Use that restricted domain so it still covers the same range. So we're going to go from negative pi halves and negative 1. So we're going to go from right here to 0 to here. So it's going to look something like this. Just a tiny little piece of the sine graph. It's a function. It's 1 to 1. It still covers from negative 1 all the way up to 1 on the range. Then it says label a few key points. Now, we want to label, let's do these three. So this point right here is pi halves comma 1. This point right here, I'm not going to write it, but it's the 0, 0. Everybody knows it's the origin. And then this point right here is negative pi halves, comma, negative 1. State the domain. What is the domain for this graph? We could drag somebody from 1050 who's never had trig, and they ought to be able to figure out what the domain is here. Squish this graph onto the x-axis. What part of the x-axis is covered? Okay, so we're negative pi halves to pi halves. Now, round brackets or square brackets? Square, because it's included. We actually included this endpoint and that endpoint. Questions? Ought to know the range. What's the range? Okay, we already talked about this several times. Negative 1 to 1. We designed it specifically to cover the same range as sine does. Okay. Solve for the inverse of y equals sine x using that two-step process. So it's a pretty easy process. At this point, we're talking about sine inverse, so I'm going to switch colors. I'm going to switch to red. So this is going to be x equals the sine of y. And how do I get y by itself? How do I solve for y? Take the inverse sine or take the sine inverse of both sides. So this would be the sine inverse of x is equal to the sine inverse of the sine of y. These two, now these are inverse functions. What do they do to each other? They undo each other, so I get a sine inverse of x on this side, and I get a y on this side. We normally write the y first, so I'm going to write, well, wait a minute. Here it is right here. That's what we're after. Okay? Now, that's a little bit silly to go through and do that. You're aware of how those inverses work. This is the function we want to graph. But again, it's that two-step process. Switch the x and y, and then solve for y. So let's graph this one. Why should this, given what we've already talked about, why should graphing sine inverse be pretty easy? We take everything that used to be an x and we switch it for y. So we just reverse those. So this point right here on the original function is an angle, then a ratio, an x, then a y. If I take that point and just switch it, I get the point 1 comma pi halves. So 1 is right here. Remember, pi halves is about 1.5, so 1's about right there. That mark's not stray, it's there for a reason. So that's 1, and then we're going to put this up here at pi halves. So about 1.5, so about right there. So on sine inverse, we've got 1 comma pi halves. This point right here on the original graph was 0, 0. What happens when you switch 0, 0? It's still 0, 0. Okay? This point is now going to be, once we switch the x stuff for the y stuff, this is going to be negative pi halves, negative 1, negative 1, negative pi halves. So that's going to be about right there. So negative 1 comma negative pi halves. There are our points. We could make this even more clear. Does anybody remember how to tell by looking at a graph if two functions are inverses of each other?
They're reflected over
They're reflected over what?
the x equals y.
Over y equals x. Now, why would they be reflected over y equals x? Why would that be like our middle, like the center of this reflection?
That's where x's and y's are
Say that again, Marcos.
Do I have to?
You- Well, that's because you've been eating rumby all period.
That's where the x's and y's are identical already.
That's where the x's and y's are the same, so anything on that line is not going to change. Anything on this side of the line is going to flip up over here, and vice versa. Any questions there? Okay, now, we could go to the trouble of looking at this graph to answer these questions right here. Or we could just remember what Javier said just a second ago. The x's and y's switched, right? So the domain, those are usually the x's, and the range, that's usually the y. So if we wanted to write down the domain and range for sine inverse, we'd take the range for sine, and that's going to be the domain. And we'd take the domain for sine, and that's going to be the range. Now take a look at that graph. Is that correct? Is its domain from -1 to +1? Yep. And is its range from negative pi halves to pi halves? Any questions there? Okay, and correct me if I'm wrong, but this is an inverse trig function. What do we plug into inverse trig functions? Ratios. Aren't those ratios? And what do we get out of inverse trig functions? Angles, and aren't those angles? Does that make sense? Okay. All right, any questions? Okay, let's take a look at the next example. On this one, we're actually going to make some computations. I do want to point this out. This textbook and several textbooks, instead of using this, and now remember, this isn't an exponent. Okay, whenever you put a -1 above a function, it means the inverse of that particular function. Okay, another way to describe an inverse is arc. In fact, when I was in high school, the very first scientific calculator I got, my mom went to the store, picked it up, got it for me, went to school. It didn't have a second function button or a bunch of the keys that you normally see. It had an arc button. And arc just meant the second function of whatever that was. So if you hit the sine after you hit the arc button, it did the inverse sine. Okay? So that's what arc sine or arc cosine or arc tangent, that means inverse cosine, inverse tangent, whatever it happens to be. Any questions there?
How often is that used now?
You'll see it a fair amount, enough that you ought to be able to recognize it when you see it. Okay? Anything else? Okay. These should not be hard problems. Haven't we seen these before? This is chapter 1 all over again, right? Okay, so coming back at you. There are a couple different ways to do this. You can have this memorized as the sine is the which coordinate on the unit circle? The y coordinate on the unit circle. So we can stop and think, well, let's see. We've got to be between negative pi halves and pi halves. We've got a positive y coordinate. Okay, so we've got to be in quadrant 1. That's going to be the long side of a 30, 60, 90. So the answer on this one is 60 degrees or pi thirds. Now, if you don't have those memorized, can you work your way through it a different way? What could we draw? We could draw a triangle. And we could count this as the opposite side, and we could count that as the hypotenuse. Again, this has got to be positive, and it's got to be drawn between quadrants 1 and 4. So this is going to be radical 3, this is going to be 2, and then again, using the Pythagorean theorem, you could find that. At that point, if you don't recognize this, you're in big trouble. Okay? Got to have that stuff memorized. Sine inverse of negative radical 2 over 2. That's going to be the y coordinate on the unit circle, or if you want to draw a picture for that, it would have to be in quadrant 4, That's negative radical 2 over 2. This is 1 on the unit circle, and that's radical 2 over 2. So what's the answer to this? Okay, 45? Negative 45 or negative pi fourths. Okay, just make sure you pay attention to the instructions, how they're asked. Do they want it in radians or degrees? Arc sine of 1/2. Inverse sine of 1/2. So the sine ratio is 1/2. I'll draw a picture for this one really quickly. There's our opposite, and there's our hypotenuse. Since that's 1 and that's 2, that's got to be radical 3, so that's going to make this a small acute angle. So we're going to have 30 degrees or pi sixth. And again, we could draw a triangle for this, or it would have to be one of those exaggerated triangles, right? Because if this is a ratio, we'd put it over 1. So that means the opposite side is 1 and the hypotenuse is 1. So how much is left for this side over here? That would be 0. So what's the angle from standard position? 90 degrees or pi halves. Notice that all of the answers that we've gotten here are all within our range. Negative 90 to 90 or negative pi halves to pi halves. Questions?
Will it always be that easy?
I wish it were always that easy. Okay. For today it might be, other than the fact we need to keep track of a couple other trig functions, and we've got a few formulas or identities that we're going to see on the next page. Okay, I'm going to go through this fairly quickly because this uses the same idea that we just did kind of in depth on the sine graph. This says find the inverse of y equals cosine x using the following steps. Same steps as we did above. Graph y equals cosine of x. Restrict the domain in a reasonable way so it still covers the range. So don't draw this. Think about what cosine looks like. Oops. Let's hope that sticks around. No. Are we going to have to reset? I hope not. Good, that's sticking around. Here's what cosine looks like. Clearly not 1-to-1. We're going to have to lop off a bunch of this graph, severely restrict the domain so it still covers the same range from negative 1 down here all the way to positive 1. What would be the best way to restrict this?
0.
Okay, 0 to pi halves wouldn't quite cut it, but 0 to pi. Okay, so the domain is going to be from 0 to pi. It better have the same range. So let's see, that's going to look like this. It's going to start off here. Good. Down to here and down to here. So here's our modified cosine graph. And I struggle with these. That looks like garbage. I'm not going to take the time to label a couple points, but we could identify those pretty quickly. I am going to draw the line y equals x on here. And just kind of tilt your head a little bit and eyeball what's this going to look like. And let's get a couple points exactly on there. This point on the original function is 0, 1. So what must be on its inverse? 1, 0. This point right here is pi halves 0. So I'm going to graph on its inverse 0 pi halves. About 1.5. And this point right here is pi negative 1. So I'm going to graph negative 1 and pi. So a little bit more than 3. So about like that. So here's what it looks like. Tilt your head just a bit. Do they look like they're reflections across the line y equals x? And should it be pretty easy to fill in the rest of this stuff? Domain and range. The domain for that inverse should be negative 1 to 1. We're going to plug in ratios between negative 1 and 1. And the range, the answers that we get out, are going to be between 0 and pi. Endpoints included. Square brackets on this one. Questions? We're good there? Okay, sine and cosine are fairly straightforward. Let's think about Tangent inverse. This one gets kind of interesting. How would I restrict the domain on this one? Is that a tough question? You can start drawing anytime, because this one, if I just draw one cycle of the tangent function, remember, we want to know that it's a function and we want it to be a one-to-one function. Well, the function part isn't a problem. It's the one-to-one that we struggle with on the other ones. If I just draw one cycle of the tangent function, doesn't it cover the same range from negative infinity to infinity? And I mean, it's like a natural restricted domain, right? Draw one cycle. Don't draw this other stuff, because if I drew this one right here, just one more cycle, is it a one-to-one function now? No. Okay? So how did we restrict the domain? Just one cycle. So from negative pi halves to pi halves. Now, I want you to pay attention to the details here. Is that the right domain? See some shaking heads. That's good. Why is that not right? It has asymptotes there. The function doesn't even exist there. So we wouldn't have square brackets. We'd have round ones, indicating that those aren't included. So we can go right up to pi halves and right up to negative pi halves, but we just can't include that. What about the range? Yep, all real numbers. Negative infinity to infinity. You can get out any ratio you want. Okay, now, if I reflect this across the line y equals x, think about this for just a second. Okay, and this is where, if you paid attention in your 1050 class, this is going to come in really handy. This line right here is x equals pi halves, right? A vertical line is x equals a number. Javier, what did you say earlier about when we find inverses? What do we do with x's and y's? You switch them, right? So instead of having a vertical line of y equals pi halves, what am I going to draw for the inverse? A horizontal line of y equals pi halves. Did I say that right? Okay. So I'm going to have another horizontal asymptote of y equals negative pi halves. And here's what the graph's going to look like. Now, again, I'm kind of speeding along here, so it's not going to look perfect, but that's what it looks like. Okay, that red one. This is y equals tangent inverse of x. Questions there? And again, the domain and range ought to be a piece of cake at this point. We just take this and switch it. This is going to be negative infinity to infinity, and the range, the range is going to be negative pi halves to pi halves. Any questions?
Is the inverse also a function?
It is. Yeah, on this one, all we have to do is do one cycle and just take that, reflect it. It's a one-to-one function, just like the original one was. Yeah, they're both functions. Okay. This one just starts out here, runs along this horizontal line, comes up here, goes through 0, 0, and right there. Okay. Anything else? Okay. We could take the time to label a couple points. Like on the original one, pi fourths comma 1 would be on the graph. So on its inverse, 1 comma pi fourths would be on that graph. Okay? All right. Go ahead and flip the page over if you haven't already. So this is just a reminder that these are the same inverse trig functions that we dealt with in chapter 1. So if we're dealing with sine inverse, it returns angles between negative pi halves and pi halves. In other words, we always get answers in quadrants 1 and 4. So there's the range for sine inverse, and here's a picture of which quadrants we'd be working in. So if you're drawing a triangle, it might be helpful to think, hey, if it's sine inverse, I've got to draw something over on the right side of the unit circle here. Cosine inverse, what's its range again? 0 to pi. That's why it's quadrants 1 and 2, not quadrants 1 and 4, like it is for sine inverse. And do you remember what it was for, I mean, we've drawn these pictures before. For tangent inverse, it was the same as sine inverse, so that's going to be negative pi halves to pi halves. The big difference is we can't include the endpoint, because the tangent ratio doesn't exist there. Okay, so now we get to the interesting stuff. So Megan asked a little while ago, does it stay this easy? And the answer to that is unfortunately no. If you're dealing with sines, cosines, and tangents, they're not too bad. But if we deal with any of the other ones, then that gets to be a bit of a mess. So let's take a look at this right here. If we're trying to find cosecant inverse, secant inverse, cotangent inverse, and so forth, you can take a look at your calculator. Will you find a button like this on your calculator? You won't. Does that mean you can't compute cosecant inverse with your calculator? Well, you can. Okay. Do you do this? Oops, let me switch colors here. Do we do 1 over sine inverse of 2? Just take that and say, well, gosh, they're reciprocals, so let's just do 1 over the sine inverse, and that should give me cosecant inverse. Javier says no. Anybody else want to weigh in on this? How many say yes, that will work? Okay, how many say no, that won't? Javier, you're not getting much support today. Okay, Javier's right. This does not work. Okay, can somebody tell me, just looking at this right here, okay, if I just highlighted this and said, go compute sine inverse of 2, what's wrong with that? No. Remember, it's not an exponent. Inverse trig functions take ratios and give angles in return. How big are the ratios that we can put into sine inverse? It's on the front page. We did it just a second ago. What's the domain for sine inverse? What is it? Negative 1 to 1. This is too big. This is saying the opposite is 2 and the hypotenuse is 1. Is there any way the opposite side can be the biggest side on a right triangle? Not possible. Doesn't work that way. Okay? So that is not the way to compute that. But we still can do it on the calculator, and here's how we do it. We do sine inverse of, take the ratio and flip the ratio over. So what's the reciprocal of 2? 1/2. Okay? Now, it's a bit more complicated when you're dealing with these 3 reciprocal trig functions. These 2 are pretty straightforward. If you want to deal with cosecant inverse, it's going to be the sine inverse of 1 over whatever we were plugging in here. Whatever this ratio is, we flip it over and then turn it into a sine inverse. Same thing for secant inverse. We're going to use the cosine inverse. We're just going to flip that over. Okay, notice what happens here, and we talked about this before. If x is bigger than 1, then its reciprocal is going to be less than 1, okay, if we're talking in absolute value. Okay. Now, in the textbook, I think there are several identities that you can use for cotangent inverse. In fact, cotangent and tangent inverse are pretty interesting because you can get mathematicians to argue about the best way to represent those. Okay? So I think the odds of something like that showing up on a final exam aren't very good. We can talk about it in class and we can do it on homework. I suppose you could see something like that on one of my exams, maybe a final exam, but it isn't very likely. Okay? The cool thing about this is we just make an adjustment. Okay, now we've talked about this before, about the relationships between the graphs of the trig functions. It's in essence, you could call it a horizontal or a vertical flip and a phase shift. That's what this is doing right here. Okay, so if you're interested in where this comes from and why this formula exists the way it does, I'd be happy to talk with you after class, but I don't want to spend a bunch of time on that one, just because it's not going to come up very often. Okay, any questions? Okay, so if you're dealing with one of the reciprocal trig functions, the inverse of one of the reciprocal trig functions, the trick is, for the most part, flip over the ratio and then do either sine or cosine. If it's tangent, then you've got to be a little more on top of things. Okay, so let's take a look at example 5. It says find the exact answer in degrees and in radians. So we want to do both. So I'm I'm hoping these aren't very difficult. Would you go ahead and write down your answer to the first two, please? Okay. I just like drawing pictures, so I know it's a sine inverse. It's going to be in quadrants 1 and 4. Opposite side is 0, hypotenuse is 1, so that means we're at 0 degrees or 0 radians, so there's the answer for that one. If it's cosine inverse, that means I've got to draw a triangle in quadrants 1 or quadrant 2. So it's positive, there's my 1, there's my 2, this would be radical 3, or if you wanted to make that one half and this 1, so it was on the unit circle. Answer here, 60 degrees or pi thirds. Arc cosine, again the arc just means inverse, so we're plugging in a ratio. What quadrant? Quadrant 2. Adjacent side, negative radical 3 over 2. That should be enough right there. If this is the long leg of the 30, 60, 90, that's got to be the short one. So that means this is a 30-degree reference angle. So the answer from standard position is 150, or quickly, or not so quickly maybe, 5 pi 6. Okay, are those easy enough, Molly? Sorry.
Yeah.
Megan? You can draw a picture for this, or you can use the identity and turn this into an inverse what? Inverse cosine, okay? Or we can just think of this as, this is the inverse of cosine, so this is the hypotenuse, and this is the adjacent. So where would we be? Radical 2, that's 1, so we're going to have 45 degrees or pi fourths. Okay. Any questions so far? What sides are involved in this ratio? It's the reciprocal of sine, so it's going to be the hypotenuse over the opposite, right? If you want to think in terms of x's, y's, and r's, that's fine. If you want to think in terms of coordinates on the unit circle, that's okay. I just like drawing pictures. I've got an arrow pointing to -1 being the hypotenuse. Is that okay? No, but remember, there are 3 ways to write a negative fraction. You can write the negative on top, out front, or on the bottom. Where should it go on this one? Has to go on the bottom. So that means the opposite side is -1 and the hypotenuse is 1. So we'd have to draw kind of an exaggerated triangle for this. Opposite side is -1, hypotenuse is 1. Where would that put us? Okay, -90 would be the right way. Not 270, right? Okay, or negative pi halves. Now, that's a cotangent inverse. If you want to use that identity right there, be my guest. Or if you want to think in terms of sides here, is that right? It's cotangent, right? Not tangent. What are the sides? Adjacent over the opposite. Okay, so let's draw a picture of what that would look like. If the adjacent was 0 and the opposite was 1, that's 0, that's 1, where would we have to be? 90 degrees or pi halves. Good? Okay, let's take a look at this one right here. Sine inverse of radical 2. How do you do that? Can you do that? No, some big bells ought to be going off. This is a sine inverse. You can only plug in numbers, ratios between -1 and 1. Radical 2 is bigger than 1. It's outside the range. So this does not exist. Okay? There is no answer to that. Because think about what we're saying here. We're saying that the opposite side is bigger than the hypotenuse. And we know that's not going to happen. Any questions? Okay, let's see if we can finish this off. We've got a couple more, a few calculator problems, and then a few interesting problems to finish up with. It says find the answer in degrees to the nearest tenth. So all we need to do is grab our calculator. It does say degrees, so we want to make sure that we plug these in correctly and have our calculator in the right mode. I'm already in degree mode. So all I need to do is, it's an arc sine or a sine inverse. Before I plug it into the calculator, remember I said don't plug anything into your calculator unless you know what to expect. Is this okay to plug in a decimal between -1 and +1? It is. That's within the range of sine inverse. So I'm going to put in the 0.78. Okay. If I were to put this over 1, that means the opposite side is pretty darn big. We're expecting an angle that's pretty close to 90, right? So let's see what this spits out. At least it's bigger than 45. Closer to 45 than, or sorry, closer to 90 than it is to 0. Okay, so our answer here is 51 point, says to the nearest tenth, so 51.3 degrees. That's okay to plug in. Does that look right? 8.1? 8.1 what? Okay. 8.1 degrees, and the reason this is correct is watch if you put this over 1 and you draw a triangle for this. This is 0.99 and this is 1. There's hardly anything for this opposite side over here. We haven't opened the angle up very much, right? Okay, can you do this one? See some shaking heads? Let's take a look. To do this on the calculator, you'd need to do a cosine inverse of, what do we do with the 0.99? Okay, we do 1 over that, 1 over 0.99. Now, I saw some shaking heads like, yeah, we can handle this one. And then I saw some other people saying, nope, can't do this one. Guess who's right? The people that said no, because watch, whoops. Watch what happens when I do 1 divided by that. 1 divided by a small number is a big number, right? We get a domain error, because if you flip that over, you're going to get something bigger than 1. Okay. To do cotangent inverse, this is going to be, now this said degrees, right? So we're going to do 90 minus the tangent inverse of that exact same angle, or sorry, that exact same ratio. So we'll just type that into our calculator. So we'll do 90 minus tangent inverse negative radical 5, 155. Okay. All right, and then a couple problems to finish off. Okay, if a problem were written like this, and I think you do have a couple like this on the assignment, it says the cosine of x equals radical 2 over 2. Okay, if a problem were radical x equals 9, what would you do on that problem? Square both sides, because squaring would undo taking a square root, right? So what do we do on this one to get the x by itself?
Inverse both sides.
Inverse cosine of both sides. So this is going to be x equals cosine inverse of radical 2 over 2. I think we did this problem earlier. What angle has a ratio, a cosine ratio of radical 2 over 2? Pi fourths or 45, right? Okay. And keep in mind, it's cosine inverse, so you'd have to have an answer in quadrant 1 or quadrant 2. So if this had been negative, the answer would be
Negative 45. Negative pi over 4.
135, 135 degrees or 3 pi fourths. Okay, because it would have to be over here. Okay, any questions there? Okay, I can guarantee you're going to see problems like this on the next test, and for the 20 so of you who are going to take calculus, you're going to see these in calculus, so make sure you pay attention to these, especially this last one right here. This is an inverse trig function, so this stuff right here better be a ratio. But if we take a look at this right here, we're plugging in an angle, and what comes out is a ratio. So we plug an angle in here, get a ratio out, and then we're going to turn around and turn it right back into an angle. So the answer to this is going to be an angle. But if you note the instructions, it says keep in mind what the range is for sine inverse. It's got to be an angle between what? Negative 90 and 90, or if we're in radians, negative pi halves and pi halves. So let's draw a picture of what this looks like. Okay, here is 5 pi fourths. 5 pi fourths is over here. What's the sine ratio there? It'd be the opposite side, right? So that's going to be negative radical 2 over 2 if we're on the unit circle. So if we did this just a piece at a time, I figured out what the inside is. Now it's going to be the sine inverse of negative radical 2 over 2. So at this point, you either need to ignore everything else that we've done on this problem and just stare at this and figure that out, which we did earlier in the class. This has to be an angle between negative pi halves and pi halves. So if you draw an angle over here that has a y coordinate of negative radical 2 over 2, it would have to be this one. And that reference triangle right there is pi fourths. So what is the measure of that angle from standard position? Negative pi fourths. So the answer is negative pi fourths. Okay, now I want you to take a good look at this. There's sine inverse. What do those two things do to each other? Okay, the best way to describe that is they undo each other, right? So whatever this one did to 5 pi fourths, this one ought to undo it, and then you'd think that the answer would be 5 pi fourths, right? But what was the answer? It was negative pi fourths, and here's why. Is 5 pi fourths in the range of sine inverse? It's not, okay? So we have to find a triangle in one of these two quadrants that has exactly the same sine ratio. Okay? So one way you could do this is draw the picture over here, flop it in the right quadrant, and there's your answer. Okay. Any questions there? Okay, let's take a look at this one. Start on the inside. Let's figure this out. 5 pi thirds. 5 pi thirds is here. We want the sine ratio for that. That's going to be negative radical 3 over 2. So here's what we're asking ourselves. What is the cosine inverse of negative radical 3 over 2? So you need to take it a step at a time because the ranges and the domains of each one of these don't match up exactly. So now we're asking ourselves cosine inverse of negative radical 3 over 2. That's a cosine inverse. It's going to spit out an angle. but it's got to be an angle in quadrant 1 or quadrant 2. So if we were going to draw a picture for this, where do we have an adjacent side that's negative? Got to be over here. That's 1/2. That's 1. You should know the size of this reference triangle right here. It's 30 degrees, so that's going to be pi 6. So if we answer this in radians, because the problem was given in radians, our answer is going to be 5 pi 6. Any questions? Okay, last one. We're almost done. Again, working from the inside out, we're going to draw a picture in which quadrant, since it's cosine inverse? Quadrant 1 because it's positive, right? If you know that chapter 1 stuff, this just goes really quickly. I don't really care what angle that is. The angle happens to be 60 degrees or pi thirds. I want the tangent of this angle right here. I want the tangent of this picture. So the tangent would be opposite over adjacent, radical 3 over 2 over 1/2. Oops. Flip that over and multiply. Answer is radical 3. Now, I'm going to leave you with this problem right here and just mention that this problem is fairly similar to this one right here. Because you'll notice we've got a regular trig function on the outside and an inverse trig function on the inside. The trick on this is to recognize this is an inverse trig function. So what does this have to be? It's got to be a ratio. Does that look like a ratio? Kind of. How do we make it a ratio? Put it over 1. So this right here is the opposite side, and what's the hypotenuse? Hypotenuse would be 1. You can draw a picture from that, and from that picture then you can figure out what the cosine is. Okay? All right. Have a great weekend.